So the topic of our group is Citybike data analysis and visualization. Our group member, I'm Yuteng Zeng, and my teammates, Xingen Chen and Zhengxuan Wen. Now let's first talk about our goal and novelty. We mainly build a user-friendly interface for our application. We designed an interface focused on user interaction with our data and our functionalities. And we provide our clients with useful insights that can serve individual needs of our users. And also we provide data visualization features. We can visualize our large volumes of raw data in an accessible format. To be more specific, we have like different charts and tables to show our results. We also implemented some very interesting trend analysis features. We can do predictions by our models, such as profit model with the hourly activity prediction and the topmost popular station prediction with random forest algorithms, and to basically serve the need of the Citybike dataset is inaccessible with their raw data, and there is no functional, useful Analyse tool for that database. So we are filling this blank. And next, we are going to introduce the data. Our data comes from the citybikenyc.com, and we use the trip data for mainly features like ride ID or start time, end time, and start location and end location, etc. And our 3 V's for our data set is we have actually pretty large velocity of the data. Since our application is deployed in the cloud, so the training basis of our data is different in volume with the actual implemented cloud-based dataset, but overall it is a measurement of gigabytes like of our used dataset. As for the variety, we consist of various types of data, such as the listed features and many other, and we can provide very good sequential prediction and analyze with such data. And in summary, that our dataset has modern volume, variety, and velocity for the application to run efficiently on the cloud. We can do more improves to the algorithms and also the platforms to make it faster in the future. And the main difficulties in processing our data is we first tested all the data set in our development environment. And we in the deployment phases, we successfully deployed our application via GCP and our app engine. We tried both ways to do, and we finally set it with the virtual machine on GCP for better performance. And the amount of data we process is about 10 million trip data. So that is mainly consisting of like 3 or 4 months of data of the total stations in the Citybike trip dataset. And when deployment, we faced issues such as in the app engine attempt, there is inadequate functions for the big data, since the resources on the app engine is limited and not adjustable to users' needs. So we choose more flexible ways to define our own virtual machine to get a better computational resources and also the better memory for our application. That is also will be shown in the latency when we are demo our application on the actual website, the latency is relatively considerably low for the user interaction. And now we're going to introduce our method. Our method consists of many use cases. To start with, we'd like to say the data ingestion. Spark allows us to ingest data from various sources, including CSV, JSON, and more. So we will be using Spark's data ingestion capabilities to bring the Citybike dataset into our environment. And also the data transformation and cleaning. We use Spark Data Frame API and Spark SQL can for the transformation and cleaning. We use these features to handle data quality issues such as missing values, false values, etc., and do the basic filtering and also selecting the invalid trips out of the total data set. As for the Spark optimization, we use Spark's distributed computing capabilities. We can optimize our data processing tasks in that case. That ensures the analysis and operations executed in a more efficiently manner. And our algorithms, they are various robust suites of building algorithms with Spark. And we applied various functions within our app from data analysis and also to efficient computations, allowing us to derive deeper insights from the data set. And now we are going to introduce technical details. To be more specific, there are machine learning algorithms we took use of. We basically, like mentioned before, we have prediction features. That is the flow prediction of station activities. It is provided in a hourly basis. We can select a hour interval duration in the future, and our app will provide a visualization on the time interval of the selected station activities. And we also have prediction functions to show the top most popular station over the day. To be more specific, we use Profit, which is a Facebook model. It can provide robust and flexible analyze and prediction to the sequential data with great seasonal adaptability, since our trip data is highly relevant to the holidays and whether the date is weekend or something. And random forest is rather more straightforward. It is used to provide a daily prediction, and it with more clear and simple features such as month and whether it is weekdays or any days of the week. So it is more explainable with its different branches in the decision process. And our pipeline is we basically trained on long-range trip data like over a year for our model accuracy. And we deployed those pre-trained model when receiving clients' queries to provide more efficient query functionalities to make the system run more efficiently.
Architecture of our system. Our web app runs entirely on the GCP and has three main parts: the front end, the back end, and the data storage. The front end is built with HTML, CSS, JavaScript, and enhanced by frameworks such as Bootstrap, jQuery, and Popper. The Flask app serves as the back end, integrating with Apache Spark for large data processing. The data, including CSV files and machine learning models pre-trained by our local hardware, such as Facebook's Profit model and decision trees models, are stored in the cloud storage. Look at the web app. As we can see in the address bar, the web app has a public IP address and it is hosted in the GCP. Therefore, the user can access and run it from any end device instead of setting up a local environment. There are 6 different functions on the left sidebar serving different purposes. Function is called BDS stations. The user can input a start date, an end date, and the number of stations to be shown. Then the function will quantify the total number of rides starting from and ends at the stations. It will output a bar chart showing the top stations with the highest traffic volumes. This function may be helpful for management of bike distribution and infrastructure planning. The function is called popular routes. The user can input a desired date range and the number of routes to be shown. The function will generate a bar chart that ranks the routes by number of rides completed. This function helps user understand route preference and traffic patterns. Third function is called station info. This function focuses on the average matrix of a single station. The user can input a station name, and choose a desired date range. The function will present an hourly activity line chart demonstrating peak usage times and trends over the day, alongside with a pie chart that categorizes bike type used, for example, classic bikes versus electric bikes. Additionally, a bar chart compares the rider types, which can either be a Citybike member or a casual rider. This function may be helpful for analyzing and optimizing the performance of a single station. This function is called the top member stations. The user can input a start date and end date, and the number of stations to be shown. The function will return 2 bar charts, which represents the top stations with the highest number of members or the highest Citybike member to casual rider ratio. The function is called predict hourly activity. The user can input a station name and the desired future date range. The function will return the prediction of hourly ride volume over the desired time range with a 95% confidence interval as the light blue shadows. The prediction is based on Facebook's Prophet models, which we pre-trained locally. The function may be helpful for predicting staffing levels and bike redistribution throughout the date range. The function is called top station predict. The user can enter a specific date and the function will predict the busiest stations on that date. The prediction is based on random forest models, which we pre-trained locally. This function may be helpful for the management team to prepare for and pay extra attention to high traffic stations on the specific dates.